Yeah, I'm Kenneth Emeka Odo. So I participated in this competition, and uh, s- there were some good parts of it where I moved up the ladder and then the leaderboard, and then at some point I fell down too. And yeah, but it was a good experience at the end of it. So I would show you what I was able to do while in this competition. So and I'll begin by what the competition is about and the evaluation metric, the winning solutions. My solution, what didn't work, and there's an extension I would also want to describe more about conditional random fields. It's a kind of time. So we'll be going deep into it. I think we have enough time today to do that, and I didn't know it before, and I saw some benefits in using it too. And there were a lot of other techniques, because actually in the competition, people were actually using papers that were published just 2 months ago. So we were published 3 months ago. So they were like the state of the art, some of the solutions. And that makes a lot of sense. That shows the competition is not just an exercise in overfitting the leaderboard. So people are actually trying to do some real research. So and yeah, so I did my grad studies in Saskatchewan, uh, and I did a number of online classes. Those days when Coursera was interesting, uh, before it became monetized. So when it used to be free, so I did a lot of classes there, and then so I did some research too, published a few papers. And I'm a software engineer. I also organized a number of meetups. So I want to make an announcement just before I proceed. I organized a study group on cryptography. Uh, like we were going to study, we are going through this book by this Stanford professor, and it's a graduate course in cryptography. So it's a very rigorous stuff on security, data privacy, and those stuff. So we're in chapter 4 and 5 this week. That's a block ciphers and chosen plain text attacks. So you can actually join us. The link is over there. Yeah, so this competition is a geology-based competition where what's geology? It's like the earth science, studying the earth crust and figuring what's in it, and the compositions of the earth crust. So this competition has, uh, there's normal classification, like you're classifying one thing, but this is like structured classification, and that means like you have like a sequence of some forms. An image is a sequence if you two-dimensional sequence of some sort. So there's a kind of a spatial relationships between them, between an image. So the point is when you mine, when you drill for oil, there are deposits of salts that occur underneath the ground. So there's a pit. Okay, I'll get to the picture later. So I should have put the picture more there. Yeah. So there are salts that occur when you drill for oil. And these salts are there like in some part of the earth crust. We'll get to the pictures soon. And those salts tend to, it's very brittle and it's problematic for those drilling the oil because they don't like the salt because it's brittle and it may cause issues with their drilling tools. So they try to avoid those areas where the salt are. So this competition is like, in this competition, you are given a number of radar images of the earth crust. So it's like a kind of a plan from the top down into the earth crust, and then at different depths. So where the salts are. So there are patches of salt. So you're given these RGB images, and your goal is to figure out which part of this, like draw a contour of the salt deposit in those images. So that's essentially what so this is a classical image segmentation problem. So yeah, and again, in this competition, some of the solutions the people had written, there are a number of methods they use. So my goal was to read the papers involved and understand them. So, and there was no way I could have rewritten it that there wouldn't be a form of plagiarism. So I just referenced, because you can't actually rename it, the methods used. So, but you can describe the process. So I made a lot of attempts to avoid plagiarism. So yeah, so in this competition, this is a well-paid competition. There were people also in the forums, and they were very angry with climate change campaigners. They said this is a project to help the oil companies, and someone was like pontificating that we should all leave the competition at the beginning. So, but the money involved is a lot. So this is 50,000 for the first place and 25,000. So despite this well-written construct, many people still join the competition. So, yeah, I understand these sentiments, but this is a competition. We are there to learn stuff. So there are 5 submissions per day. External data not allowed. So this is a well-paid. This is like 1 year salary if someone wins the first place. So many people ignored the advice of the climate change campaigner. So now the leaderboard, there were a kind of changes in the leaderboard. So this is the private leaderboard and this is the public leaderboard. So someone was describing, because someone was doing some leaderboard probing and realized I realized this lately in the competition. If I had known it much earlier, I would have done much better. If you are able to, in a leaderboard probe, someone identified that 25% of the images have no mask in them, no salt deposit. So, and most of those empty masks confuse your training. It adds a lot of noise. So, most of, if you see all the winning solutions, their goal was just to do a kind of intensifying where the signal to detect where the salt is. Some went the route of having a separate classifier to identify when there's a salt or no salt. And because I realized after my all my models, there were a lot of this dissonance in the data points where there was mask. So it's like it's noisy. So this predicts this. So there's a lot of noise where you have empty mask. So people who understood that very early in the competition designed their model to undo that.
Was there a difference in the test distribution and the training distribution in regards to this?
Actually, I didn't check how many was in the training set, how many empty masks actually. But from someone who did leaderboard probing showed at least 25% of the images were empty in the test set. So I didn't do on the training set to see what it is. Yeah. So now and then I think people's scores got better in the private leaderboard than in the public leaderboard, and some people actually fell down the table. There were a lot of movements in this competition. So there's a lot of movement down, even in the winning solutions. So those who, now you see like I finished in 0.83 and the winning solution was 0.89 and I was in like 1,000. So it's like, so most of, this is a very tight competition. Every bit mattered. So I would explain a lot of what people we are doing and reasoning behind some of those steps, what can work in production and what can make sense, and things that are just only competition specific and doesn't add much more value outside the competition. So, yeah, so I borrowed this slide from Matt, the other Matt. So just a little bit of the segmentations we are trying to handle. So I think we are doing this kind of semantic segmentation. So just like the same, only sort you're identifying. You're not like, you're not doing instance segmentation. So this is the one we're doing. So I just wanted to, so if, like in our context, like this may be like the salt. So there's only one kind of salt. We are not told to identify different kind of salt. So semantic segmentation. So now this is the earth crust. Yeah, or a possible form of an earth crust taken from a side view. Just imagine the earth just elevated, and then you're having a side view of the world, of the earth from where you're standing. So this is just, I saw this from one of these papers. So yeah, you can actually start seeing amber salts. This is on the ground. So in many places where there's oil deposits, they have a number of salts there. So you can see salt deposits on this. Like, so somebody wants to drill through. So you see there's a salt here. So they try to know where the salts are. And someone actually said it's a proxy for maybe, okay.
I was just wondering whether a lot of the data came from like, what do they call tectonic, like continental crusts or oceanic crusts? Like, I know they do a lot of drilling for oil in both.
I'm not an expert in geology, so I only just took this slide just to show the views. I'm not an expert in geology.
My question is also kind of related. Maybe you can answer this one. The company that put this challenge up, is this a company that is interested in finding salt? And they essentially just...
No, actually, I think it's a project because they actually involve in like data analysis for oil companies. So I think maybe they were trying to figure out some kind of figure out one kind of task that would work for something else. So this is just like to see what techniques people are using. That's what actually the person who was complaining about climate change was against. He said it's a prodigy competition. So because if it's only identifying salt, they won't bring out 50,000 per year. So, but yeah.
You might answer this in a second. Is it intersect over union that's the score?
Yeah.
Okay.
So intersection over union. We mean over ranges. So because of the way this data was collected, so you'll be better off if you create your local CV, having this depth in form of your validation, arranging it in that form. So there was some coverage and stuff. Those are specific to geology, so we shouldn't discuss that. Yeah, so using just the depth to do your cross-validation on your local validation set. Because actually the first thing in a competition you want to do is to understand the metric, the evaluation metric, and then try to create a pipeline from start to finish. And then see if your local CV looks a little bit like very close to this public CV, public score on the leaderboard. So I think that's the first step you do before doing this competition. So that took me a while also to get that pipeline going through. So yeah, but then at least I got to some few decimal places.
Sorry, I may have missed this. You're saying you're stratifying using depth. So you have an image and you have some metadata that goes along with that image. Okay. What other metadata do you have aside from depth?
Oh, only depth.
Only depth.
Yeah. So okay. So actually, in the data they had like 400 images and 18,000 images. So and it's just 101 by 101 pixels. So each image has a mask. So it's just like an image and a mask. So it's a very little data set to build very sophisticated models. Yeah. So that shows you maybe they had other plans too for this. But maybe if data collection is expensive, they want you to get a model that you could make use of the minimal data they have, so they could apply it for another problem that they're having too. That's kind of similar. So that makes sense for them. So the submission format is the run length encoding. So this is
Sorry, the training set is having lesser data than the testing set?
Yeah. So I think why they did it that way, they want you to do model that will work on minimal data. Maybe the data collection is expensive in their domain. So and maybe they have a side project, they want to apply the techniques from this competition too. So they want to see how you do well on small sample. But there's a likelihood of overfitting because of the minimal fitting the parameters in some of the complicated methods people were using. But they have a way of validating it because they have 18,000 images too to see how well you did. So I think it was a success on their part because the scores were like intersection over union 0.89, so which is almost like F1 score in some respect. So the competition lasted for 3 months. 3 months and so this is a description of how the image may look. So this is just like a rendering of this is an image, and this is where the salts are, for instance, in this image. So it's even difficult for the human eye to identify where this is. So, for instance, in this image, this is an image at a depth, at a specific depth. So, and this is where the salt is. And so like in this image, for instance, you see there were a lot of white. So if you're learning colors, for instance, there's nothing in this. This has no salt patches. So so definitely gray steel as a pre-processing will make sense. You don't want colors like So this just shows you in one chart everything, what the data looks like. So now this competition is based on intersection over union. So this is basically Jaccard coefficient. So, but now you now have different thresholds. So because you're actually passing in two binary images for comparisons. So the foreground and the background, 1 and 0. So these are the thresholds with which you convert your images. So you do this for these sets of thresholds from 0.5 to 0.95, and make an average of it. So when I was trying to see what's the mathematical justification for that, it looks like precision recall curve of some sort. Maybe they're simulating stuff of that sort. So which is almost like a ROC of some forms. So yeah, so that's how I think it to be. I'm not a mathematician, so I'm not a statistician either. But that's what I could reason from studying the metric. So now the first place solution, they had made use of ResNet and ResNet. So ResNet is a paper that has been inspired by the ResNet. This one was there before. So this is just you have a skip connection from an input, and then you do some processing in between. So it could be some batch num and other stuff. So you're just taking a circle through passing part of the data in. So, but in ResNet, you have, in this one, like you have like, in ResNet, you have like one block, and then you make a skip connection. But in ResNet, you have multiple blocks and of similar behavior. Then you have the skip connection that you're adding at some point below. So they said they should have the same, from their paper, when I read the paper, they should have the same structure in the blocks that you're settling. So the reasoning behind it is if you keep increasing the depth of your neural network, performance can improve. Performance over the test, like prediction, may increase. But after some time, you hit a brick wall, diminishing returns. So even though you're increasing the depth of your neural network, you are not getting any performance boost. And then if you say you want to increase the width, maybe you're increasing the size of all the widths. And that also has another boundary. So then the goal is to not increase the width or increase the depth, but now have these sets of blocks that are like similar, and then with these skip connections. And then for some reasons, it works better with the vanishing gradient problem, and so it solved a lot of existing problems in the past architectures. So this guy used it. So BC is binary cross entropy. So this is just an entropy score.
I may be jumping ahead a little bit. So this looks sort of like a UNet.
Yeah, we're based on units. But people are customizing different encoder and decoder part.
For sure, but the center with the feature pyramid attention, that looks something like more from a mask RCNN thing.
Yeah, because I read what that means. It's master, because what they mean by that pyramid, it's just like a field of view, like a kind of a pyramid field of view. So you have different layers. So it's like a delegate convolution of some
It's
forms.
looking at features at different resolutions, basically, and putting those
together. Because I read the paper,
Okay.
actually, of that. So I think it's a Chinese author that had written that paper. So that's basically, it's more like master RCNN. But the attention part, I couldn't figure out how it all fits in together in that paper. So I was looking through that paper, and for a while, it was a new paper, actually. I think it's 2 months ago. I think it's one of those postdoc guy or PhD using part of his PhD work for a competition.
So this whole network doesn't have its own name, because it's not quite UNet, it's not quite mask RCNN, it's something else, but
So it's a modified UNet.
modified UNet?
Yeah, so the UNet is like the base of some form. So then they modify the encoder, and then the decoder, and then the center part they use.
It's the center part that's the most different from a normal
Yeah.
unit.
So the center part is.
Interesting. Okay.
So they didn't release their code, and someone was trying to, because I was going through the code to try to replicate some of what they did in the script connections. So, okay, you have a question.
No, you keep on talking if you need to talk.
What? Someone was asking a question about raising his hand. Yeah, go ahead. Oh, sorry.
Mine's a fairly simple one. What library did they use for this? Was it like TensorFlow or PyTorch or?
Oh, they didn't release their code actually. So people were trying to replicate their solution, and I was trying to replicate it too. It took me a while. So, but I only got to 2 levels because they had 3 levels. So.
And what is this tconv in the decoder? Next to, so it's conv 3x3 and then tconv.
What's it? I can't remember what it is. I was actually focused on these two. So.
Transpose convolution.
Oh, the transpose convolution. Okay. Yeah.
A transpose convolution, which is just like, that's an inverse convolution? You're not supposed to say it, but.
It's sort of symmetric with
Yeah.
the way you down.
Yeah. So these people actually worked on, after building their version of UNet that they customized with different kind of encoders. So this part, these hypercolumns, because I read the paper and also Wikipedia on that. So it's what is it, virtual cortex? It's a closer way of simulating what happens in the human eye. So it's so they added that part, and then squeeze this SESC is spatial channel squeeze and excitation. So after in CNN, after going through your filters, when you move through your filters, you get feature maps. So usually people don't touch the feature maps that much, but in squeeze and excite, you wanna intensify the important part of the feature map and then reduce the less important part. So there's some form of scaling and some operations you perform across all the channels and then some within the channels. So the goal is just to dampen things that are less important. And it worked well for them. So, yeah.
So is this something where the model learns the parameters for the squeezing, or is it just like already set and you change them as hyperparameters?
No, the model learns it. Yeah, from the paper, the model learns it. Yeah. So and then there's one zoo where you can get things. It's GitHub. So Lovar score is actually a direct way of optimizing IOU. So that's so yeah, I had a few issues using Lovar score. Somebody introduced it in the competition, and then I couldn't get it working because my values are out of whack. And then I realized the last layer has to be a logit. So, and if you use softmax, okay, you have a question.
A comment. I found the paper about this model. It's called Pyramid Attention Network for Semantic Segmentation, and it just came out in July this year. So it's the new thing, I guess. And just a dumb question. We're talking about squeezing channels, but this is just one channel data, is it not? Are there multiple channels?
Yeah, there were multiple channels, but people threw away the other channels. I threw away the other channels.
Okay.
So I don't know if he threw away the other channels in this case.
Yeah.
So because he didn't release his code, so we're only trying to replicate what he did.
Right.
So I will show the experiment. We were trying to see to understand what he did. So and so yeah, some stuff in hyper stuff. Yeah, and what was I? So this is a direct way of optimizing the IOU. So I think it's a Canadian author who wrote this. It's a Canadian research group. So I looked through that paper. So they are optimizing it directly. So they have multiple stages. So if you look through what they were trying to do, is like they had multiple stages. So the first stage, you have these inputs like a UNet, because UNet has been described a lot in this stuff. So I don't want to put any slide on UNet anymore. So it's overused in this meetup. So it's like you have this input, and you after predicting all those outputs from your unit, the first layer, now if you see all these 5 folds, this shouldn't be used like in production really, because what it is like in a neural network, I don't see why you should be doing that. It's like you take like 4 folds, you train on one fold, you have one model. You train on another part of the 4 fold, so you now have 5 models. And then you now assemble the results from those 5 models. So the performance boost, because I experimented with some of those, the performance boost is just like 0.01, 0.02 people. But in Kaggle, people need those tiny bits of, so sometimes I believe it's like random noise or it's not significant. So, but many people are doing that. So, and it gives them some boost. And then there's what they call snapshot learning. Snapshot learning is if you were in the past in the Meetup when they do distillation, this is a way of assembling neural networks. But it's, rather than assemble the prediction, you're assembling it at the weights. So you extract all the weights, and then create one base model to do one kind of moving average updates on the entire weights, training with a cosine learning rate. So what the cosine learning rate is usually most people tend to use like kind of annealing, where you like reduce your learning rate over time. But that's very bad for saddle points. Okay, there's local minimum and there's a saddle point. So let's start from what those two are. So if a local minimum is a real turning point, it's not a false one. Let us use that. So it's a real turning point. So you can actually see that in the second derivative. Yeah, but when you're using gradient descent, you're basically you're not going to the second derivative, so you will not be able to see directly. So, but now, the saddle points, if you reduce your learning rate, like on those saddle points, you get stuck there. So, but now when you use a learning rate with a sinusoidal waveform, something that undulates. So, and if there's some parameters you have to tune on the cycle, the length. If you are lucky to have this match, the crest, all the ascension points on your saddle points, and those reduction points at those local minimum, you'll be able to escape the saddle points. So because I did a lot of experiments on those kind of cycling learning rate. So the point is you have your learning rate will follow a cosine waveform. Yeah.
A question for you, Matt. This reminds you a lot about the fast AI. What's the learning rate thing that he's using?
Oh, one cycle.
One cycle, yeah.
Yeah, so I think it might be similar, but
Yeah, it's the same. It's based on the paper by Leslie.
Okay,
Leslie,
perfect,
same
yeah.
based.
The question I have is about that input where they upsize to 192 and then pad. It seems very weird that they wouldn't just upsize straight to 224. Did they say anything about that?
No, they didn't give any information on why they did. So, yeah, and actually, increasing the data size to some point will improve your performance, and there's a point you get stuck. You don't get any performance boost by increasing it anyway.
I think it might just be to fit into the ResNext. I'm just not sure why they didn't go all the way.
They didn't put the size of the machine too, because it may be also memory constraint. So I think it's more of a memory constraint, maybe of sort.
A speculation on why they padded to 224. They wanted to put a little boundary around it because in the UNet architecture, you lose a little bit every time. So they wanted to keep all the data all the way down to the lowest level.
Oh, I see. Okay. Yeah, so that's, we've gone through snapshot and Lovasco. So this is just having dice coefficient. Dice coefficient is, it looks a lot like, what's it called? Intersection of unions, but there's a, is it an approximation of the F1 score where you have two dice? It's, I think so. Yeah, so I'm not sure, but it's similar to those. So they just combine the two together. So because, yeah, and now in this competition, okay, I forgot, there's what they call multi-label and multi-class, if I'm meeting it. So if you're having a okay, let me just put it in layman's term that I can understand. So if you have like a possibility of having two classes from a final layer, possibility of two classes. So you shouldn't use the softmax there. So yeah, because if you use softmax, then you're spreading the probability across all that last layer. So you're better off using just sigmoids on those parts. So you're modeling each independent one. And then you look for a good threshold to help you make that classification. So I didn't know that earlier on, and I figured that out in the competition. So yeah, so this is just what they did. And then, yeah, they squeezed on the side. Okay, we've gone through those. Yeah, the assembled stuff. The five-fold stuff or fold stuff is not something. And, okay, they've not done about the pseudo labeling. Okay, we'll get there. Yeah, so now, okay.
So on your final layer, so I'm trying to understand the thing that you learned. So originally you had two classes that you were predicting, and then you softmaxed that, and the classes are just 0 or 1.
Yeah. So
Okay.
you spread the probability across all the possible outputs. So
would that be equivalent of just predicting 1, 0, or 1 with one sigmoid?
yeah.
Okay, so those two things are similar, and what you found worked best was having two classes still, and each of them being a sigmoid activation.
Yeah, of those sorts, so then you can threshold it. So with like if you have your F1 score, F2 score, you just use that for figuring out the best threshold.
Okay.
So now what they did is like in the first layer, they actually got some samples. So but now they want to intensify what are the signals in their in the images. So they threw away all these predicted pixels that were not activated. So they reduced their samples for the second round. So that was what they did. So that's why I realized that why they're doing this is basically because they just want to intensify the signals in the data. So they're doing multiple stages. So this is basically like each pixel you have in your image. Maybe if you want to check what ranges are they. So is it between 0.25 and 0.8? What numbers are between that range? And then the total number of pixels. So they now choose those. If they trust a particular threshold that they think is reasonable, they didn't put the threshold they had used to make that decision. So if it's something reasonable for them, then they use that to train the next network. So yeah, and then they continued with. So I think we now have understanding of the unit and this transpose convolutions now. Yeah, it's here now. So yeah, and this hypercolumns thing is the first time I saw that. So yeah, I tried SendNet. It didn't work for me, but somehow it's how you in these competitions is usually how you manage to combine different techniques in one full chunk. So now some people came up with the idea that rather than just segmenting right away, what about classifying first and then segmenting later? So yeah, and so there's some people were using there's a binary cross entropy for classification, and then so now after they do the classification, they now take in the first layer of the network and the last layer of the network and bring them together for the lowest score. Now the point is, when you do that, you have to be sure, because you are using sigmoid, so you have to convert it back to logits in the loss function for lowest score. So I had that issue too in the competition.
Okay, just a quick question. What are they classifying? Whether there's like any salt?
Yeah.
Okay.
For each pixel.
So each pixel, but then why do classification then segmentation?
So there's a discussion on it on the forum. So people were saying they got better results doing it that way. So I don't think it's an alchemist thing. So I think it's a design choice. So, but the point is, once you've done that so you have to be sure that you are having the logic before checking this loss. Otherwise, your values will become so large. And so I had that problem for like a week, and I couldn't figure out what the issue was. Until then, I started reading the paper on Lova's score. And then after reading the paper, I now saw, oh, this is what it has to be logic at that point.
I'm speculating again because I don't know what this Loves thing is, but I'm guessing maybe they do the classification just to get a soft estimate, like not a hard 0 or 1 binary.
We need
2 mics.
Yeah, so I just looked it up, and it's just a way of being able to directly optimize IOU, because IOU isn't differentiable, but this Loves is, or Loves, however you pronounce it.
Yeah. Okay.
Do you think one of you could explain? I'm just going to ask you, Mike, so that's what I'm getting into, but why you're skeptical of the idea of the classification versus segmentation for it?
It just, to me, like, if it's by pixel, it doesn't really make sense, because essentially what a segmentation is by pixel classification. But if the problem is we have a few of these images that have no salt at all, and you want to separate those out, then it would make sense to do classification. It's just not clear to me.
Yeah, so this is just the augmentation that they did, the random brightness, contrast, and stuff like that, and some assembling. So let's go to the next one. So the ninth place one, it looks, so there is so now people noticed that if this Lover's hinge loss, if you make it symmetric, you have an improvement. So symmetric is just so taking the average of everything flipped. So this was a trick someone actually posted, and I said, oh, this, because I'm trying it in another experiment I'm doing right now. So, it's much better than using so now I now know that there's something that called Louvas. Someone's trying to make it symmetric. So, so that's what this is all about. So this stochastic weight averages, it has all the links to snapshots. So where you have this, and so rather than combining a number of prediction of your neural networks by the output of a prediction, you want to combine them by the weights. And then, so this stochastic weighted average is the process that you go through that snapshot. On the last layer, made the kind of a moving average, and then use a cosine stuff to go around it. So that's what you have a question. Oh, okay. So then, so that's what this place is. Yeah, so the other part, deep supervision, I was supposed to read, I just forgot to read that part. So, but it has 3 losses, one for segmentation, trace. I didn't read the paper. So people were discussing it on the forums, and I didn't understand what it meant, what they mean by deep supervision. It has 3 losses. So for some reasons, I didn't remember to look it up. So, so that, so there are a number of stuff. So there's something known as cutouts. Usually in some image like salt, because you saw in the image that you could look at this image and not know that there's a salt there. Maybe there's an occlusion of some forms. So now in cutouts, if you're doing as an augmentation in cutout, it's like you want to simulate having occlusions on your images. So so this is one trick too for if your data has that kind of properties. So you may want to look towards that as one of your stuff. So there are snapshots on this. So someone actually used the fast AI course for determining learning rate. So fast AI is getting popular. Everyone uses it in the forum. So then the loss. Deep supervision has 3 losses. So that's classification, segmentation loss, and a kind of a total loss, the combination of everything. So, so the 5-fold, I already explained what the folds are. And so then what I did in this competition, so everyone began with a vanilla unit. So that gives you some 0.5 or 0.6 on the leaderboard. So, and then you now want to say, oh, this is not good enough. So how can I go further? So I came across a concept known as adding dilations to the unit to try to intensify the signals. Dilated convolutions on the unit. And I got some improvements. Yeah. So, and but that wasn't enough to go much further. And then standardizing the image, converting it to be like between zero in a standard distribution. If you have subtract from the mean and divide by the standard deviation, that worked better than dividing by just 25. So in most of my cases, and I realized like using cyclic learning rate. Just then I didn't know how to choose learning rates because I haven't taken the fast AI class. So but now when I took the fast AI, I said, oh, this is how you choose. Yeah, but it only showed you how to start, but not the other range of the data. So yeah. So now, if you're using cyclic learning rates, you should be careful not to try like reduce on plateau. So because you don't combine two policies that are not compatible. So it's like you're trying to form a sinusoid and then you're trying to dampen it to follow like a different stuff. Yeah. So and then if one thing I realized if you're saving the best model as you progress, there are two things you have to consider. Because like in the first AI course, they said the metric is not so important, it's just to print. But I don't think so, it depends. If you have the metric and you are actually doing model checks, like model saving as a validation of your metric, then you must make sure that there's a correlation between your metric score and the loss it should be positively correlated. Or because I also had similar issues. So it has to be positively correlated. So that means when you plot similar values, you should have like a kind of 45-degree stuff. Otherwise, if you're optimizing on that, you'll be doing so worse. You'll be doing worse than you can anticipate. Yeah. But if you're not optimizing with your metric score, validation of your metric score, you could use anything. So the printout it just based on your validation loss alone. So I figured that out. And then if you're like validation loss, sometimes it's better to run for longer epochs if you're always saving the best at different point in time. So even if things get worse, you had already saved the best model while your process is reading. So those were some of the things I figured out while working on this. So because my goal is to understand the maths behind everything and the theories, not just copying code. So and then so this was some of the stuff I use. Sometimes if you try early stopping, you may stop your process before it improves at some point. So and then I came across what they call conditional random field. So this was much better when if your score is like less than 0.5, it can give you a boost to close to like 0.79. But after that point, you reach the threshold, you can't improve anymore on that. So and that's why I had to spend some time on discussing that. So yeah. So and then the assembling technique I used was basically just averaging the averaging stuff and just thresholding it by the average. So weighted one actually, weighting it by the local CV score for each model. So that worked much better than just an average. So I weighted it by the local CV score. So that was my result. Yeah, so this was luckily for me, I didn't need the heater because it was heating up my room. And then I figured out a way of running a number of experiments, and I use bash scripts to run my Python scripts, so that when I'm sleeping, it doesn't stop all my experiments. And so I did more than 100 experiments and validating a number of hypotheses. So you begin with doing one at a time. Okay, increasing this, what will happen when you do this? How would this score be affected? So a lot of it, and then diagnostics. So debug through all the logs you get. and look, okay, maybe my learning rate is too high, and then you see from the logs, you can actually see log everything. So, and then because it's useful for like debugging. So, yeah, so those were, yeah, what didn't work? I tried FFT on the data, and then I realized it wasn't working. Maybe the phases were important. Of course, it should be. So I tried focal loss, but I didn't get any improvement. And then some other people tried a number of networks like Darnet and other stuff, pistol shuffling, which didn't work for them. Then pseudo labeling had missed outcome. So what is pseudo labeling? Pseudo labeling is a way of regularization, as it's called, where you take some of you build your model first, you run everything through your initial model, and then you make a move to predict using your test set. And then after making prediction on your test set, you now use your test set and then retrain your model again. So, and now the problem with using this method is I tried to do some of those. It doesn't give so much boost so far. I don't know if people are getting a massive boost from it. But in Kaggle, if it's just 0.01, that's a huge boost. So because that can be the difference between like 10. But now the difficulty is how do you tune it? So what's the sample size you have to take of the test set, and how? So it's very easy to fall to the victim of information transfer between your training and test set if you're not careful with tuning it. So, and in production, it's also hard to reproduce the experiments. So you have to be very careful when you use pseudo labeling.
Back to your FFT, did you do an FFT over the entire image globally? So you didn't do it in little blocks and then look at the...
No, I didn't do it in little blocks. Maybe that would have been better. But I was believing if I had done it across, then the CNN would have done the little blocks for me.
Yeah, perhaps. But it does seem, the FFT approach seems like a reasonable thing to try because the salt deposits seem to be kind of flat-ish, and there's the stuff that isn't salt seems to be quite high frequency. But I would think you would want to do it in little blocks to identify where the salt is or not. But anyway.
Yeah, I think, because in another experiment I was doing later, I figured out how to split out the images into different parts. Then I didn't know that. So maybe it's part of future things I learned that I'll be using in future work. Now, so yeah, someone was saying the organizers arranged the examples for the leaderboard. So the ones that have more economic sense were the ones given for the leaderboard. So people could focus more on those. So maybe sometimes overfitting the leaderboard may be good for the business in some forms. So that's what someone was trying to insinuate. So, yeah. And someone was saying don't trust CV, trust stability. It doesn't. So, but what he actually meant is just trust the local CV more than the leaderboard. So, yeah, and then someone was in the climate part. So these were the most important thing in the discussions. So in the approaches, what basically most people had done form of augmentation, some form of upsampling, and then building the model, the variation of encoder-decoder kind of architectures. And so sometimes people change the amount of dropout here and there, add batch num here and there, add some form of attention here and there. So all those is just perturbing the model itself. So they're just trying out different things on it. And then some people try to perturb part of the data too. So this is like having a kind of like FTT, all those stuff on the data, and then running it through this stuff. And then some people tried out post-processing. So that's where the conditional random field came in handy. So it's like you have some predicted mask, and you want to enrich it and make it much better. So that's why they tried this. And then thresholding is just the way you turn it into binaries and downsampling. And yeah, usually people did a number of assembling and yeah, the weighted of some forms. Yeah, so definitely there are a lot of like the way people were doing augmentations. So there are a lot of augmentation that worsen your results. So I realized if you use an augmentation that doesn't model the distribution your data came from, you have worse results. So there's a rule of thumb. So yeah, like if you feel like horizontal flip was a very good one in this competition, because most data sort can occur in either the left or the right. There's no restriction on why the sort that's on the right hand side cannot go to the left hand side and vice versa horizontally. So, but people had issues with vertical flips. So yeah, some people, yeah, so maybe understanding the domain will help you. That's where domain knowledge comes into. And yeah, there's some existing libraries I think that are much better to use. Because if you do some augmentation by hand, it's easier there's some transformations you may do. You don't want to do them together because you're deforming the object itself. So you want to like choose one of those. So I realized at some point that I was having a number of issues. I realized I was actually deforming multiple transformations that shouldn't go together. So yeah, so this is also something you should also consider when working on that. So now we move into conditional random field. So let me see if we have, okay, we still have time. What's the key again? I just view. No, I just want to. How do I do? What's the full string?
Command L.
Oh, Command L. Oh, okay. So conditional random field, it's suitable for structure prediction. So actually, if you have a data that like image where you have so many correlated pixels, so most pixels look like the neighbors that's closest to it. So you don't just want to assume that they're independent. So that would be very bad assumption because you're throwing out all these relationships between them. So if you use things like naive Bayes, you're assuming independence, which is going to destroy things. So you're saying all pixels exist independent of the other, which is not true. So now adding edges between them to capture those is more cumbersome. So it's even hard to figure out what edges you could have. So now using some Bayesian formulation, you want to convert like kind of a joint probability of what could be like a generative model into a discriminative model. And yeah, so then this slide goes to what they call deep distribution. So deep distribution is a topic from physics. I have a background in mechanical when I was much younger. So it's like you have particles in a system. So it would be like heat, like maybe convection molecules vibrating in a channel or somewhere. So you want to find the probability of it staying in different states within that system. So yeah, and there's this relationship with the energy of the system and the temperature of the system. So the goal is to exploit those states and try to model how this image changes to the mask. So that's essentially what you're trying to do. So you want to model the process, how each pixel from the given image transforms itself into the mask. So you want to model that entire process. So as you taking them to be like particles from physics. So one particle is moved to another place. And so like they call this scope in that material, but this is actually just the state, just a configuration. What input led to one output. So that kind of combination. So yeah, so this is just like this is just a normalizing term, and you want to have this kind of joint probability. So this is like your output. So what input led to the output? You can have conditional distribution, conditional probability, and then this is an unnormalized. No, this is unnormalized. So you just want to normalize it to be probabilities. So this is just the beginning aspect. So I want to show how it relates to logistic regression, and then show how it relates into image analysis, if we have time. So yeah, so in that class by probability graphic models, the Stanford woman. So she's trying to show that there's a relationship between conditional random field and logistic regression, for instance. So if you take a very simplistic case of logistic regression, where you have like just one parameter to tune and an indicator variable. So where you may have something like, okay, if you have an input, you have only binary inputs and binary outputs. So your input and output will be 0, 1. So this is a very simplistic case, just to show a special case where conditional random field may degenerate to logistic regression. So it was designed to lead to that output. So it just, yeah, if you take, this is an exponential of this. So if this is 1, so the value will depend on what the value of x is. So if x will be 0 or 1. So and then you normalize across the multiplication across all the variables and get a probability distribution. So, and this looks like a sigmoid. So this is a sigmoid actually. This is just like the parameters you have as a sigmoid. So, because if you see logistic regression has this sigmoid form, that's what you use to classify things as 0, 1, binary classification of the sigmoid. So that saturates input to between 0 and 1. This is a squeezing function, as they call it. So, yeah, so under some conditions, so now the benefit of this kind of modeling is you don't have to have all the inputs for the output because of that conditional distribution. So you could use minimal data to do that. So, yeah, so the applications of conditional random field. So you usually use it for structural predictions like maybe you have a sentence and you want to get all the parts of speech on that sentence. So it's like they're almost the same size. So each sentence have a part of speech that maps to it. So similarly, if you have a mask, each pixel is there salt on it, on the other part of it, so that you're predicting the mapping between these inputs and the mask of like where the salt is and where the salts are. So those are the kind of problems where conditional random fields are good for. So it's like, yeah, the mic is there. Okay. Matt.
Of course.
So it's kind of blowing my mind a little bit. Is what this is trying to do is you have a whole bunch of, like, say, point measurements or something like that, and you're
Yes.
trying to decide if this is like part of the salt based off of all the neighbors around the salt?
Yeah, so we'll go into that. So I just started from the very simple one of logistic regression, and then we'll be opening up a new page where we'll be looking at a real image segmentation and going to the maximum a posteriori kind of stuff. I don't know if we have time for that. So, but
It's 7:37 right now.
okay, yeah, so we have some time. So, yeah, there's this slide. It's I think UC Berkeley. So they were actually describing how you use it for image segmentation. So because the implementation, most people base the implementation of conditional random field on this library, which is based on this paper. But understanding this library, we may have to read this class notes and just a very quick overview. So maybe when you look at the code, sometimes it may not be so complicated anymore. So, but there may be a little bit of maths. So, but we'll be very fast about it. I don't know if we have time, but yeah, we try and accommodate that in some form. Yeah, so this is just like your Deep's distribution, this first part. So W here, in this slide presentation, they had this, they abused notations a little bit. So W is like a state. So a state would be like an input that maps to an output. So like, that'll be like XY. So you just assume it to be in that point. So then we now go to like, so what this means is that there's no state that is inadmissible. What this means is that for like, you can move from one, that every state has a probability of being reached in the system. So that's what this just meant, this means. So now this G here, so this is like, on each pixel, you are trying to see the neighborhood of that pixel to predict that. So G is like all the neighborhoods of the pixel, so except that pixel. So that's what this part just means. So, and then the Bayesian formulation, and then this is the probability of being in that state. So this is normalizing across all the states. So just to give you an idea of what they mean. So now, they now did a kind of a starting a kind of trying to figure out how to move from this image to the segmented image, and trying to model the process that may have led to the original image or segmented image based on how you go through the arrow. So now, if you're going this route, so that means you have a true image and you want to get a segmented image. Or if you go through this route, that'll be like you have an image you want to restore to the original image. So now the goal is to model the process that may have led to F, and this process that led to it. So that's what you're trying to model. So they made some assumption of like a Poisson process and stuff like that. So yeah, so this is just a modeling two states. And this is the state, a state of the image and the process that may have led to it. So this is purely theoretical in nature. So this upper part is the energy of the system. So this energy of the system you could parameterize it in some functions that you may know. And this is the temperature of the entire system. The temperature is assumed to be constant across the system. You have a constant temperature. So the goal is, the observed image you may have seen has the real image with some noise in it. So at some point you want to model what the noise is too. So when you look at the code, it may not. So this is like a kind of overview of the maths that may be involved, that's involved in it. So this is just a number of base. So this is like the neighborhood. So you're just taking like conditional probabilities on those neighborhood and base formulation. So it's on the slide. So yeah, and So they tried to model the noise and they made it optional. So even though they had modeled some of the noise and added this term here, the slide was trying to make things complex. This is the easiest description I saw on the internet. So and that's because the paper is not accessible. From when I read it, I couldn't understand it. But I understood this material better. So this is just like the energy you parameterize by this object. So you don't know what F is. So the goal is from a maximum a posteriori optimization, you want to infer what those are. So that's just the idea. This is just normalizing stuff. So this is the energy, this is the temperature from physics. I'm not a physicist, but I did mechanical engineering. So thermal convention, we all did thermodynamics. So it's from thermodynamics concept. Yeah. So the goal is, you don't know what this or this is, but you know the neighborhood and all these inputs are. So you want to get the one that maximizes this value of these two. So now you may need something like the gradient descent that may interpolate from one place. Sometimes there's a clever way. You may start from an already segmented image and use it as an initialized vector form, and then start doing the optimization towards that, using that as your optimization there, because you start from something random a bit. So, but it's better for you to use something that makes meaning, not just random. Maybe something you segmented that you want to enrich to be much better. So that's just essentially what it is. So you're just trying to figure this two out. So now, from this description, if you look at the code or the paper, then it will become clearer. Yeah, do you have any question? So this took me a while to wrap around, but I think if you look at the slide once more.
So would this have the effect of smoothing out the boundary between salt and not salt?
Yeah, that's when the thresholds are between less than 0.775 range. Yeah, someone was writing about it in the discussion forums. So, but the person didn't know why that was the case. So, but after reading through this, to the maths description, and then that became much clearer. So I think I don't have I still have a few slides, not to Control L. Yeah. Okay. Let me put this 1 minute. Okay, so yeah, so there are the way people handle large data in this competition. So people tend to like reduce the data size, use smaller batch, or crop the image and train different part of the image and aggregate them at the end. It was in the past, the last competition I went for, I had this constraint on my hardware, but I now realized the problem was because I didn't understand generators properly. Generators gives you these iterators that you can just call nest on. So you could actually, because you're using as minimal data as possible. Once your data is saved in disk, you won't run out of memory if you just sample only the amount you need. So which is, once you have this epoch per samples and you can just be sampling from that part. So only the amount you need that is, it's an iterator. A decorator is an iterator that only gives you the current value you need. So a dictionary is the form of a generator too. So in Python, it's just a generator that you can just, so you're not saving things in memory, you can just call a nest on that and get the data you want. So you can actually not be sampling only the amount you need. So you won't have so many memory issues, like running out of memory. So I figured that out in this competition and why that exists, because you can run as, and in the new project I was doing too. So I also found batch norm to be more computationally expensive than dropout. So I also realized too in this competition, using batch norm and dropout worsen your result together. Yeah, so there's a paper on it. So because a batch norm tends to try to balance the distribution across all your batches. Batch norm, okay, dropouts now add some kind of noise. So those two noises worsen performance when you use them together. So in this competition, I figured that out. I didn't know that before, but the learning competition. Yeah. So what many people did, as I've discussed, people tried to figure out a model that predicts salt or no salt, and then on those ones that predict salt, kind of use all your models on those ones and do some aggregation. And so there's this paper. So the paper that describes why these two should not be used is in this. So actually, in the past, some experts have actually built the networks using those two, but this paper describes why that's a bad idea. So you could look it up. So, and I also realized if you have a unit and you are systematically reducing the dropout as you go through the encoder, you tend to get better performance. If you reducing them at a constant rate through the like encoder-decoder structure. So, yeah. Then, of course, upsampling tends to, because if you're doing like dilated units, for instance, there's some expectation on your size of inputs. So sometimes the bigger the input to the image, the better your performance in most cases. So the upper limit would be memory constraints that you may have. So I think, then these are my contacts. So, and you have the links on the Meetup app, so you could check it out. So I'm done with my presentation. So these are some of the thoughts I gave over the past 2008. So, it's in one place. So if you have any questions.
You covered a lot of material here. That was great. Do you feel like you learned a lot, and are you excited to go into another Kaggle competition at some point?
Yeah, I'm going into one right now. This, what's it called? This cell stuff. But yeah, I just started it. So I'm trying out some of the stuff I learned from this into that one.
It was more comment that I really liked that, what was it, CRF?
Yeah.
What was it? That form of trying to map to the masks, because with a lot of these competitions, sometimes it's just a lot of boosting layers, a lot of convolution layers, just throwing GPUs at it.
Yeah.
And, so I really like this approach.
Oh, I see. So people use it for like enhancing actually. But you could also use it also from the entire prediction if you want. But maybe people use it for like enhancing. So